Hi everyone. We're going to continue on our conversation today with covalent bonding. We're going to focus on polar covalent bonding as well as non-polar covalent bonding. I also want us to just look at the formula of how we would calculate a dipole moment, and then that will get us into talking about different characteristics between ionic bonds, covalent bonds, as well as metallic bonds. So we looked at this part. I think this is where we left off last time. So in covalent bonds, we know that atoms share a pair of electrons, and we talked about how there are three major electrostatic interactions in these bonds. So there's a lot of repulsions that are happening in a covalent bond that we don't really ever think about. So we know that there's an attraction between the electron and the nuclei, but then I also have repulsions between the electrons, but then I also have to think about the repulsion between the two nuclei. So if I wanted to look at an electron cloud or an electron density model, I would look at this part here on the bottom part. So I see that the two nuclei are here. It's probably really hard to see that on your screen, but it's a little bit darker around each of the nuclei, which makes sense because I'm still going to have some of the electrons then that are going to be closer to the nuclei, but then I can see that it's also a little darker just here in between because that's where the actual bond is being formed. So the concentration of the electron density between the nuclei right here is that covalent bond. So we said that there's two types, nonpolar versus polar, and bond polarity is going to play a really big important factor or a really big important role when we're talking about molecular geometry, which is the next chapter. Specifically, when we say bond polarity, I mean, is something polar or is something non-polar? So we said before, or you already know, bond polarity is just a measure of how equally or unequally the electrons in any covalent bond are shared. So in a polar covalent bond, one of the atoms is going to exert a greater attraction for the bonding electrons than the other atom. And in a non-polar covalent bond, we know that they're going to share that attraction equally. So if I'm comparing two covalent bonds, I have fluorine molecule and then I have hydrogen fluoride here. So for fluorine, I have an equal distribution in terms of how they're attracting that particular set of electrons or that pair of electrons. So they share it equally. Both fluorine atoms are pulling on the set of electrons equally. So that would be a non-polar covalent bond. In hydrogen fluoride, I know that ultimately fluorine is going to take or share more of the electron pair because it's more electronegative than hydrogen will. So the electrons are going to be more focused on the fluoride end than on the hydrogen end. So this would be a polar covalent bond. If the difference in relative ability to attract electrons is large enough, then this is how we will form an ionic bond. It's really not non-polar, polar, ionic, and there's this huge cut and dry difference between all of them. It's more of just a spectrum. So I want you to think about going from non-polar covalent bonds to polar covalent bonds to ionic bonds as a giant spectrum instead of thinking about them as three separate things, okay? So if I have a more electronegative element or a more electronegative atom, and it's large enough in its electronegativity difference, then ultimately we're going to form an ionic bond. So this gets us into electronegativity. And electronegativity is the ability of atoms in a molecule to attract electrons to themselves. So remember, this is different from electron affinity in that electron affinity is the actual addition of an electron to the atom versus electronegativity is just the ability to attract the electron. So that's the difference between the two, and we can't mix those up. So if I'm looking at a general trend for electronegativity in terms of my periodic table, we increase in electronegativity as we move from the alkali metals toward the halogens or toward the noble gases. If I want to talk about which element has the highest electronegativity, that would be fluorine. It's at 4.0. And the one that has the smallest electronegativity would be francium, even though that one's not shown on here at all. It actually just ended here at cesium. So according to this one, it would be cesium, but really francium would be the least electronegative. So electronegativity will increase as we move from left to right, and electronegativity will also increase as we move from the bottom to the top of a column. So if I want to say that in a different way, it will decrease as we move down a column. Why does electronegativity increase as you move across a row? It increases because as I'm moving towards the halogens, and we know that the halogens are one away from having that full octet. So their ability to attract an electron so that they can fulfill that outer shell is very, very high, which is why the halogens will have the highest electronegativity. So same thing with oxygen family. The oxygen family needs 2 electrons, so their ability to attract electrons is still fairly good. Not as good as the halogens, but still fairly good. So as I'm moving this way, it should increase. And then as I move down a column, it should decrease. And really electronegativity decreases as we go down a column because now we're adding more and more energy levels, we're adding more and more shielding. So because we're adding more shielding, we are decreasing the Coulombic attraction between those outermost electrons and the nuclei or the nucleus. So because it doesn't have that much of an attraction, really whether or not it gains an electron is kind of diminishing because of that effect. Okay, so looking at this, I can kind of just use the difference in electronegativity between 2 atoms to determine if a bond is going to be nonpolar covalent, if a bond is going to be polar covalent, or if a bond is going to be ionic. So the greater the difference in electronegativity between the atoms, the more polar their bond. And really, an ionic bond is the most polar that we could get. So if I'm looking at fluorine, I have an equal distribution of that share